how many of you wish you could bring your laptop to your exams? Anyone? Yep, plenty of people, and so do I. So imagine for a second your brain was as fast as a computer. What could you do? You could ace that math exam, tweet and tag people on Facebook in real time, and have all of Wikipedia to use at your disposal. So, that is a motivating example. It would be great if our brains were more like computers. We do so much. But take this image of a cat. What do you guys see? Like a cat? Are there any associations with the cat? Yeah. So we have associations, memories, representations for this cat, and something meaningful. What do you think the computer sees?
Cat.
Cat. Well, I wish the computer would see a cat. It just sees a bunch of ones and zeros. It's just arrays of values and RGB values. So if you're going from this picture of a cat, how are you interpreting it? What are the steps you take to know that, yes, this is a cat?
The color, the ears, the eyes.
The eyes. Yeah. Yeah. So you'd say you're imposing conditions on the cat. You're like, it has these features, therefore it is.
Yeah.
Well, that's kind of similar to how the brain works, or at least how the basic unit of the brain works, a neuron. Today I'm going to talk about compositions of these neurons called artificial neural networks. And my talk today is specifically how these infer things, how we can make inferences in the world. And this is relevant in tagging on Facebook, Google Translate. Most self-driving cars right now are using this technology to drive behavior and recognition. So here we have a neuron. We have many inputs. Here are dendritic spines. So in our brain, we have 100 billion of these things. Very low power, very efficient. And from our neurons, we get inputs. If we meet some sort of condition, kind of analogous to a cat, let's say we have incoming neurons and let's say the 5 neighboring neurons fired, so we've reached some threshold, therefore we send the signal down the neuron. And that signal propagates down the neuron to many outputs. And each of these neurons has thousands of inputs, hundreds of outputs. And it just keeps propagating throughout the brain. But the underlying thing for this is we have one basic unit which is able to impose a condition and transmit the signal further. It's kind of like a function. You take an input x, based on what the input x is, you produce some result. There's some logic happening there. So, as a motivating example, although it's not a cat, something that's difficult for computers to do is recognizing digits, right? Just like a cat, you identify the whiskers, the type of tail it has, the colors. You have similar properties for a number, right? So, how do you recognize numbers?
He doesn't know them.
Yeah, but visually, like, what do you see about a number? Like, how do you know this is an 8?
Because he has two circles.
2 loops, yeah. You'd say that's identified pattern. Now, say I removed this component over here, like that trailing edge. What would it look like then?
In S, basically, kind of S way.
Yes, or like a number. It would be a 6 or a 5. It's open to interpretation. So, from a computer's perspective, we take input, and this is just a bunch of pixel values, intensities, grayscale, right? So we take those as our inputs. At the hidden layers of the network, so a neural network is just a composition of the neurons we saw earlier, we can identify patterns. So you can kind of think of this intermediate layer as representing those properties. Yes, it has a loop. No, it does not have a loop. So as a similar example, so I give you a 9, right? And how would we construct this 9? So you could say it has a top loop plus some bottom loop, right? And these two together form a 9. How do we form an 8?
2 loops.
Say 2 loops plus 2 loops. So in an actual neural network, in these hidden layers, you can think of each of these neurons as imposing that condition. Yes, the input image has a loop somewhere. Yes, it has like a line. And if we have a certain amount, like it's a recipe, we can compose them together and get a classification out. So in the output layer, we get a digit. So we have a loop, we have a line, 9. We have 2 loops, up, down, and it's an 8. And it just travels through this network with each intermediate step, performing a logic function on this. So that's the underlying intuition again. So we make inferences, whether it's the cat or digit. We extract features from it, which are represented by intermediate layers. And that's the firing or not firing of individual neurons. That composes patterns, and we do this through a process in machine learning called training. I'm not going to cover that today. And then by matching these patterns together, which is just a bunch of conditions, like the way me and you interpret images, we're able to make some sort of inference. So it's a very systematic way of doing things, all underlying the actual circuitry the brain uses, the neuron. So I was telling you earlier about these features, so this is an actual trained network. You can't see any of it, so I'm going to zoom up on it. So you can see earlier how many of these features that we see in digits are actually exposed here. So the reason there are more perturbations in the actual image you see here is because 9s aren't always like this. They can be sideways, upside down, very badly drawn. My handwriting is awful. So from here you can see like individual features. Like here, you can see a 1 kind of, like a 2 kind of, 9. You see individual loops. And through a composition of these, you're still going to get the digits. Now just imagine we're feeding in images into the network. We can extract similar features. And that's how most modern image classifiers do. So using neural networks, so before this was a very difficult problem. Like the most we could do was get like maybe 50% of the data set right, just like making guesses of classifying images. Modern neural networks can get accuracies above experts in recognizing everyday images. So here, various images, classifications, and your confidence levels. So that's just classification. You told me earlier it was a cat. Like that was like obvious enough. But could we like associate things with it using neural networks? One step further, we can actually do scene recognition. So it's kind of wild to think that like a computer could actually do all of these things. Given an image, an individual scene, pixels, extract some sort of meaning from it. But the computer is not thinking, it's pseudo-thinking. It's just performing the computation on all these conditions, and they're matching them together. And through all that conditional matching, you can get some really complex behavior and do some really amazing things. So last thing I was going to do, time allowing, and I do have time for this, is I'm going to show you a live demonstration of neural style, which is based on neural networks, but uses a feature of the training. So I guess I can just show you guys like this. So here we have a picture, right? And I'm going to choose a painting to style you guys. Okay, so when this completes, you're going to see your guys' like faces in the style of some famous painting. And this is all happening in real time. It's because we can match these conditions and patterns. Like you have a famous painting, right, or a famous artist like Van Gogh, and like he's going to have a distinct style. And you can match all of this together and actually make inferences the other way around, like generate things. So that's a bit about the magic of neural nets. There's a lot more to this. There's the aspects of training, making more abstract predictions, recurrent neural networks, so we can actually extract more meaning from things. And overall, neural networks are going to play an integral part in the future of computer science and engineering. So I think they're a lot cool.